Welcome to this lecture exclusively for understanding the Rx and Ry regions. Even though a little bit of this has been explained earlier, but I would like to show it more visually so that you can understand better when you have got pictures before you. Let me give you the formal definition of Rx and Ry, but let me also tell you what's the scope of the discussion. I will formally define what's an Rx region and then visualization of an Rx region, then a formal definition of an Ry region, visualization of the Ry region. Then what happens when we are having a situation where the region is both Rx and Ry, and how do we resolve this tie? Then there is this advanced concept of region segmentation. So we will have to understand when it arises. And then all this cannot be understood without suitable illustrations. So in this presentation, I'm going to take you through all these things, beginning with a formal definition of the Rx region. Before that, why are these Rx and Ry regions being given so much importance? Because it helps us in performing Cartesian double integrations efficiently, particularly when the limits are not given. So understanding Rx and Ry regions would help us determine the limits of integration based on geometric considerations, which means the figures become important. But let us not finally say that Rx Ry region concept will solve all our double integration problems. So let us formally define an Rx region. It is a region that is trapped between two vertical lines. And you know vertical lines will have equations where x are constant, with lower and upper curves not intersecting each other. So there are two issues here. We have got vertical lines, then there is a lower curve and an upper curve between these two vertical lines, and they are not supposed to intersect. Only then the region is called an Rx region. Let's look at our first visualization. Look at this region. It is a region between, say, an elliptic arc and a straight line. And this region has been trapped between two vertical lines that you can see. One is the y-axis and the other line parallel to the y-axis 4 units away. So that is between x is equal to 0 and x is equal to 4. So you can see that between these two vertical lines, the lower curve, that means the straight line, and the upper curve, which is the elliptic arc, they are not intersecting. So to make things very clear, let me show you very systematically. So begin from there, that is your left vertical line, that is the right vertical line, and just observe whether the region under consideration is trapped between these two vertical lines with the lower curve and the upper curve not intersecting. That is very important. Between the verticals, the lower and the upper curves will not intersect in an Rx region. Having understood that, how do we express the Rx region mathematically? So you can see, I write it as Rx, then use a square bracket, then write x limits first, which are constant, x is equal to 0 and x is equal to 4. Then the lower limit of y is the lower curve, in this case the straight line. I have written that as y is equal to 3 by 4 into 4 minus x, and the upper curve as y is equal to 3 by 4 into square root of 16 minus x squared. So you don't have to worry about these y limits because the equations are provided in the question itself, and your job is to only write y as a function of x for both the lower and the upper curves. This is one of the simplest Rx examples. Little bit of complexity here. I have got a region trapped between a parabola and the straight line x is equal to 4. And then you can see the region is trapped between that line, which is x is equal to 0, and that line, which is x is equal to 4. Then you can see the lower branch of the parabola, which is the lower curve, and then the upper branch of the parabola, which is the upper curve. They are not intersecting. So even this falls under the purview of an Rx region definition. So write your x limits first, then the y limits next, with the lower curve coming first and then the upper curve coming next. We have two more Rx region situations. This is a region between the y-axis, a parabola, and a straight line. And you can see once again that the left vertical line and the right vertical line are having the entire region between them, with that as a lower curve and that as the upper curve. So therefore, you write the x limits first and then the y limits. And don't be worried how I wrote that x is equal to square root of 17 minus 1 by 2. I got that by solving the two equations. So you will learn that while we are practicing the problems. But what I want you to understand is the concept that Rx regions are those regions which are trapped between vertical lines with lower and upper curves not intersecting. This is the last scenario where Rx regions can be visualized. Here is a region between two parabolas and sliced off by x is equal to 1 and x is equal to 2. So you can see the region is trapped between these two vertical lines, 1 and 2. Then comes the lower curve, that's number 3, and then the upper curve. And I have written the limits exactly in the same order. So these are the four Rx situations. The limits of an Rx double integral will appear like this. The outer integral will carry x limits and the inner integral will carry y limits. Of course, y limits are functions of x. And how do we get it from the diagram? It comes like this. You can see the lower limit of x is coming from the left vertical line. I didn't show here, but the upper limit of x comes from the right vertical line. Then how do I get my lower limit of y? It comes from the lower curve. And how do I get my upper limit of y? I get from the upper curve. This is how you fix the limits of a double integral. An Ry region will be easy now because it's just a rotation of the Rx region. It is a region that is trapped between two horizontal lines. And you know, horizontal lines in Cartesian geometry will have equations where y are constant. And obviously, when the region is trapped between two horizontal lines, we talk about the intersection of the left curve and the right curve. So that intersection should not happen. So in an Ry region, the region is between two horizontal lines where the left curve and the right curve will not intersect. So let us look at four visualizations of the Ry region. This is the easiest one, where we have the region between an elliptic arc and a straight line. And then you can see that the entire region can be visualized as trapped between two horizontal lines. That is the lower horizontal line, that's the upper horizontal line. Those will be the y limits, they are constants. Then comes the left curve, then the right curve. The left curve will be written as x as a function of y, and the right curve will be written again as x as a function of y. So Ry regions are expressed mathematically the way you're seeing below that graphic. The second Ry region looks like this. And then again you can see that region is trapped between two horizontal lines. One of them is y is equal to 0. The other is y is equal to square root of 17 minus 1 by 2. So again, that is the lower y, that's the upper y, which are constants. And then this is the left curve, right x as a function of y. Then that is the right curve, right x again as a function of y. So you have to maintain that discipline. Y limits should be lower first, upper next. X limits left first, right next. Then we'll have the third visualization of an RY region. Again, this region is trapped between two horizontal lines. That is the lower horizontal line, that's the upper horizontal line. The equations are y is equal to 0 and y is equal to 4. And then come the left curve, then the right curve. In this case, the left curve and the right curve are the two branches of the parabola itself, because the parabola is running through the diagram. So you can fix the limits exactly the way you are seeing down. Now comes the last case where we have the region between two parabolas sliced off by y is equal to 1 and y is equal to 2. And then this is how I understand my limits. That is the lower y, that's the upper y. This is the left x, that is the right x. And again, you fix the limits exactly the same way. So these are 4 Rx visualizations and Ry visualizations. And then the limits of an Ry double integral will be something like this. Observe carefully. In an Ry double integral, you will have y limits first, then the inner integral will be having x limits. And then how are you getting the lower limit of y? It's coming from the lower horizontal line, and the upper horizontal line becomes the upper limit of y. Then how do we get the lower limit of x? It is the left curve. And how do we get the upper limit of y? It will be the right curve that you are seeing. Suppose the region is both Rx and Ry. Then we say it's a tie. So how do we resolve this tie? The choice is yours. You can do anything you want. You can choose to express the region as Rx or Ry, but choose that one which will make the process of integration easy. So don't get fixed that I want to express everything as Rx. The problem may look simpler if you put it as Ry or vice versa. Region segmentation is an advanced concept in this discussion. And when does it arise? There can be situations when the region of integration is neither a simple Rx nor a simple Ry region. That means between two vertical lines, there are intersections, or between two horizontal lines, there are intersections. So then you have to definitely break up the region into segments. So you may break up the region as an ensemble of two or more Rx or Ry regions. So you can break up according to your convenience. You make it 2 or more Rx regions or 2 or more Ry regions. But if you apply common sense, you must keep the number of segments minimal, because more is the number of segments, there will be so many integrations you'll have to perform within the same problem. So be wise to consider only that format where the number of segments is less. Now you will see after this, because this is a very, very valuable presentation, because you have understood the region analysis, and then unless we see suitable examples following this, this may not make sense at all. So I'll be showing you in a systematic way the examples that will make you understand each bit of this presentation. Thank you very much.